what an atom would look like if you were looking at the atom's perspective, of course. Let's get this started with. Today, we're first doing atoms and nuclear physics. Green! Let's get to start with, people. Now, atoms and nuclear physics is an interesting subject because of how it seems to shape itself towards the world. Atoms are the fundamental building blocks of nature. Oh, God. They're the fundamental building blocks of nature, and although they are not used they're not shown actually like this, they're more like blobs. You can actually use this way of model so that you can go ahead and be able to not so accurately, but you can actually go ahead and do experiments with it, because if you oversimplify this, then the world will just make more sense. It's very useful, and then you'll be able to make advancements in fields, which is why even though quarks are not points in space, and they're not actually that shallow, we say they are because it helps us move forwards. It's a story of the point particle. Then we have atomic and nuclear energy. Now, atomic and nuclear energy, this is just one of the more fundamental things of physics and atomic energy and atomic physics too. And it's also about nuclear physics too, because if you look about it, you can technically put electrons into orbitals, and each orbital wants to be filled up with as many possible electrons as are. If all the shells, all the orbitals of the atom are full to the maximum point of atoms, then it's great, and which is what all the noble gases have. However, as you move to the left of the periodic table, less electrons are in the last orbital, and they need more electrons so that they can add in. For example, the leftmost column here, the alkali metals and hydrogen, the alkali metals, they basically have only one electron in their outermost shell. Not saying they only have one electron, but they need a lot more electrons than these elements to be able to fill up their groups. And I like to think of it as if it was a feudal system. Noble gases we're the kings. We don't want to go ahead with these filthy peasants. And filthy peasants will literally do anything they can to rise up their ranks and get money. Electrons are money, and noble gases have the most money that they can have. Yeah, that's what I actually imagine it like. Also, the lower you go, the more unstable they become, and boom, they're gone before you can even use it. And of course, when they're gone, sometimes they split themselves and they shoot out these sorts of protons and neutrons. Alpha, beta, or gamma particles, as they're called. Alpha particles is the radiation that's the least strongest. In fact, all it does is shoot out the helium nucleus, the equivalent of the helium nucleus. Also, it can the alpha particle can easily be absorbed by a sheet of paper. Just to be safe, use 2. Or just to be safe, use 5, to be honest. And the beta particle, well, it's just basically another particle by itself. They're electrons or positrons. Positrons are just the positive versions of electrons, and they cannot be absorbed by a thick piece of paper, but it can be absorbed by a thin piece of metal, like copper, for example. And the most dangerous type is gamma rays. Now, these cannot be absorbed, unfortunately. It can be weakened, but it can't be absorbed. Gamma particles are just dangerous. They're electromagnetic waves. Thin sheets of metal and thick pieces of paper cannot block it. Well, thick pieces of lead can just have it. Make it as half as strong, but it's still dangerous even though it's half as strong. And this is what is called a radioactive decay. It decays the nucleus so that it becomes stable again. Sometimes the natural process takes thousands of years, while other times you can actually man-make this decaying function, which makes uranium and plutonium atomic bombs possible. And then, of course, radiation is very dangerous, especially gamma radiation. So you basically have to wear this protective suit that can block as much as possible, but it's not a permanent solution, though. It won't permanently protect you from gamma radiation, which is why they put these dosimeters on there. The line you see under the numbers right there gets darker as more gamma radiation hits it. So when it gets the darkest, it's game over. Your radiation suit won't help you anymore. And the uses of radioactivity is actually one of the greatest advancements in science. In fact, how you can use it is like you can use it for making electricity, renewable electricity too. Also, it creates a lot of waste that's very dangerous to throw away. And we've all seen the Hiroshima power plant. Where's the Nagasaki? Yeah, he was the Hiroshima power plant. The Fukushima power plant. Fukushima. And we can even use it to destroy cancer. We can use it for weapons. Unfortunately, we can use it for weapons, but we can also use it to see into space. If we can't even use cosmic radiation background, the radio background, the cosmic microwave background, basically as it's called, and nuclear fission and fusion. Fission is basically when you split the atom in half by shooting out a neutron at it, and it starts a chain reaction. And neutrons are split. When you put a neutron in an unstable atom, the unstable atom splits and it also shoots out 3 or more neutrons, which in turn hit other atoms that are also unstable, and then in turn they also split 3 or more neutrons, and so on until there's no more atoms to actually hit. That's what nuclear fission is, and that's what the A-bomb is. However, it's very, very, very ineffective. Fusion, however, is more. However, when we tried to make fusion plants, though, we needed to put in more energy. If we needed to put in more energy than the output gave us. So what is fusion anyway? It's when you throw 2 protons or electrons at each other, and usually it bounces off back, but they're hitting each other so hard that they fuse together into one atom, and it gives off energy, or use that energy to either create a very, very strong bomb that's even stronger, that's like 15 times stronger than the A-bomb, or we can use that to create electricity that has no risks. And even if it melts down, it'll just instantly cool itself because it won't be going at that speed. It won't be like a nuclear meltdown, fortunately. And I already told you about power from nuclear reactions. Those nuclear reactions can create lots of electricity. In fact, the whole world is most likely either using one form of energy or another just to power themselves. And that's all I have for you today. So until next time, shout out, peace. Fission fusion.